Welcome back to a brand new part. Part 3 of exponential and logarithmic functions is understanding logarithms. This is a brand new word for us. We've not studied it in previous years. We didn't look at it in previous topics. So logarithms, what are they? In our first topic with function transformations, we talked about the existence of inverse functions. That's way too big a highlight. So all mathematical operations have inverses. So the opposite of, or the inverse operation to addition is subtraction, inverse operation of multiplication is division, and correspondingly, the inverse operation of division is multiplication. They are inverses of each other. Exponents have inverses too, and that is specifically a logarithm. So our exponential function says this. It says y is equal to c to the power of x. If you want to take the inverse, we know that we swap x and y. And thus, a logarithmic function can be said to have this form. But we don't like that. Y is not isolated. We like having y isolated. That's how we know how to graph things, right? We make our table of values, maybe, and we choose some values for x, and based on them, we get values for y. And y is that dependent variable. So how on earth do we isolate y? That's where we express it in logarithmic form, like so. And it is very necessary to be able to go between these two forms, to be able to see that y is equal to log base c of x and turn that into x equals c to the y. So we'll want to be able to go between those forms with ease and comfortability, because they do mean the same thing. Now there are restrictions on the base. When we had exponential functions, we said that the base had to be positive and it could not be 1. Similarly, we still have that base. Oops, that's an eraser. Yep, there's that base c. It's still the base. And that restriction still exists. So c has to be positive. C will not be 1. Anything else is fine. Now, if we say that y equals log base c of x, we can say that x is c to the power of y. That's what it says. Another way to phrase that is to say that y is the exponent that is applied to c to attain x. So, looking at all this, c is the base, y is the exponent, x is thus actually a power. So a logarithm extracts the exponent from the power. That's kind of what it does. Now c might not always be written. If it's not, that's called the common logarithm, and that's base 10. So we're going to try some of these. There's a number of ways to go about doing this, but for us today, we might want to just write these in exponential form. So log base 2 of 32 is like log base 2 of, well, if we could express 32 as a power of 2, it'd be something. We've got like 2, there's 4, there's 8, and there's 16, and there's 32. Sweet. 32 is 2 to the power of 5. So then we start asking ourselves, well, what exponent do you put on 2 to make it 32, right? 2 to the power of something equals 32. What could that be? Well, now we're asking, 2 to the power of something is equal to 2 to the power of 5? What is that? Well, it must be 5. Again, the logarithm extracts the exponent from the power. As long as these bases match, we good. So what exponent does 2 need to turn into 2 to the power of 5? That's just 5. I quintuple dare you to try these other 5 and see where it takes you. I'm, of course, going to jump right in as I tend to, but you have the freedom to pause. Hey, whoa, there's no base written here. The heck? Oh, right. C's unwritten. It's got base 10. So we can say this is log base 10 of, hopefully 100 is 10 to the power of something. Oh yes, it is. 100 is 10 to the power of 2. So what exponent does 10 need to have applied to it to become 100? 10 to the power of something is 100. That's 10 to the power of 2. Log base 10 of 100 is 2. On I go. We zoom in. I'm going to rewrite this. Log base 5 of 5 to the power of something. 125 is 5 to the power of 3. Therefore, log base 5 of 125 is 3. This one, log base 9 of, okay, how do we write 9 as a power of 9? 9 is 9 to the power of what? Hopefully you can identify that as 1. Therefore, the exponent that 9 needs to turn into 9 is just 1. Add 2 more, right? Whoa! How on earth? You don't have to write all these steps, by the way. You can just straight up jump straight to that answer. That's cool. You can also do that here. Realistically, this might appear as a multiple choice, maybe? Who knows? But we will take this in steps just as we ease our way into it. Log base 4 of 4 to the power of something. Oof. Well, for starters, we can say it's 16 to the negative 1. And then if you want, you can say that, well, 16 is 4 squared. But most ideally, you can already see that 1/16 is 4 to the power of negative 2. And thus, log base 4 of 1/16 is negative 2. And final one, log base 7 of 1 is log base 7 of 7 to the power of something. 7 to the power of something is equal to 1. Survey says it's 0. 7 to the power of 0 is 1. That's how these two statements are equivalent. So what exponent does 7 need to become 7 to the power of 0? That's just 0. And what's worth noting there is, just as anything to the power of 0 is equal to 1, you can also say that no matter what the base is, if you're taking the log of 1, that's equal to 0. So these statements are equivalent. Of course, that is a side note. That'll probably get mentioned again on the next page. Anyways, that's that. And we can use that same translation, in terms of the words being used, not in terms of shifts, like in transformations. But we can use that to solve basic logarithmic equations. Because, remember that log form, log base c of x equals y, all these components exist where this is a base, this is an exponent, this is a power. Again, just restating this business. So y is the exponent. So this value here is the exponent. We could phrase this as saying that x is equal to 4 to the power of 3. Right? This is my base. That's my exponent. Whatever the log is equal to is the exponent. In which case, 4 times 4 times 4 is just 64. That thing is done. Quick, try the rest. There's no time. I dare you. Quintuple dare, I guess, again, because there's still 5. Again, you can pause. So do that. And I'm going to do this. Did I say? No, next line. X is equal to 3 to the power of negative 4. That's the translation. That's how to turn one into the other. That's the equivalence. Which in this case means that x is, if you want, you can write the step of 1 over 3 to the 4. What's key is that you can identify that that's 1 over 81. This is, of course, all non-calculator, so be aware of that. Ooh, this one looks fun, a fraction-y fraction. According to the equivalence statement, x is 16 to the 5 over 4. Yoicks, how do we deal with fractional exponents? Oh, I know. I'll turn it into a root. There's that coming up from grade 10. Never thought you'd see it again, did you? But you did. In which case, I can say that the 4th root of 16 is 2, which means I haven't addressed this exponent of 5 yet. And then 2 to the 5 is 32. Blah. Whoa! There's no base written here. Who made these notes? What were they thinking? You know what? They're probably thinking that it had a base of 10. Because when no base is written, it is assumed to be 10. Don't forget that. So in this case, x is equal to 10 to the power of 8. X is a 1 and then like 8 zeros. Nailed it. No, I did not nail it. Nailed it. There we go. And just a couple more here. In this case, 5 to the power of 4 is equal to x. I'd write it in that order personally. So x must be 5 times 5 times 5 times 5, which is the same as 25 times 25, 625. And lastest example, x is equal to 2 to the power of negative 6. You can write that x is 1 over 2 to the 6. Don't turn this into a 4 straight line. Therefore, x is 1/64. Learn your powers of 2. They are like the best powers. They're up there. That's all the examples we're going to be doing. So again, make sure that you can convert this way to be able to evaluate a logarithm. That's very necessary. And then this conversion where you turn a logarithmic statement into an exponential statement. Some things that we may have noticed as we were going through this include all this. This one we noted in that one example where we had, I think it was log base 7 of 1. So this thing corresponds with this cheese right here, where we said that anything to the power of 0 is 1. Therefore, you can use this rule that's hard and fast. Log base c of 1 is 0. So no matter what the base, if the power has a value of 1, then the exponent must be 0. This one we saw in the example with the 9. We had log base 9 of 9 and said it was equal to 1. And that's again because if you apply an exponent of 1 to any base, you'll just get the same thing back. This next one is pretty much the same rule as what we applied in the first part. What exponent, here we're saying, what exponent does C need to become C to the x? Well, it needs x. If you put the exponent of x on C, then it becomes C to the power of x. Hence, this line right here. And then this last one says that if you take C to the power of log base C of x, you get x back. How does that work? Because log base C of x is the exponent that C needs to become x. These rules are 1000% worth remembering. Some of them might be on your formula sheet, like maybe this one's on there. I honestly can't remember. But these rules are extremely useful. And, oh, apparently they're also fun. Who knew? In any case, there is some practice work that you'll want to do. So make sure you go ahead and do that. Really get familiar with logarithms because they are a brand new concept. So you'll want to anchor that down. We will be looking at other ways to play with logarithms. We'll be looking at their functions, and then we'll like the graphs of their functions, and then we'll be looking later in the year at some more logarithmic equations and such. And it's going to be pretty much the best time. That's all the lesson for today. I hope you enjoyed it. I have no idea how long this was, but hopefully it was a reasonable length. Yeah, okay. Well, bye. Stop.